Welcome. In this video, we'll cover acid-base titration, what it is, why it matters, and how it works. You'll also learn to calculate concentrations and interpret titration curves. Let's get started. What is acid-base titration? Picture this. You've got an acid and you've got a base, and you want to know how much of one it takes to neutralize the other. That's what acid-base titration is all about. So we can say an acid-base titration is a method of quantitative analysis for determining the concentration of an acid or base by exactly neutralizing it with a standard solution of base or acid having known concentration. Okay, time to geek out a bit. What makes an acid and a base? We've got three theories here. Arrhenius, acids give off H+, bases give OH-. Basic, Bronsted-Lowry. Acids are proton donors, and bases, proton acceptors. Lewis, acids accept electron pairs and bases donate them. Sounds like teamwork, right? Let's talk about the VIPs of titration, strong acids and strong bases. They completely dissociate in water. Acids drop a bunch of H+ ions, while bases flood the place with OH-. This complete dissociation is what makes them so reactive and perfect for titration experiments. Next, we will go through to acid-base titration curve. The titration curve shows how the pH changes during the reaction of strong acid titrate with strong base. Before the equivalence point, the solution is acidic. However, at the equivalence point, the pH hits a perfect 7, neutral. After the equivalence point, the solution becomes basic as there's more base than acid. Next, let's explore the titration curve to understand what happens when a strong base meets a strong acid. Before the equivalence point, the solution stays basic because the base is in control. At the equivalence point, the pH hits a perfect neutral, 7. Beyond the equivalence point, the solution becomes acidic as the acid starts to dominate. This curve gives us a clear picture of how the reaction progresses step by step. Let's look at an example. You have 50 milliliters of 0.05 molar hydrochloric acid, and you titrate it with 0.05 molar sodium hydroxide. We will calculate the pH 1. At the start, initial point with just the acid. 2. After adding 10 milliliters of sodium hydroxide. 3. After adding 25 milliliters of sodium hydroxide. 4. After adding 30 milliliters of sodium hydroxide. Step by step, we'll figure out how the pH changes. Here's how the pH changes during the titration. At the initial point, the solution only contains HCl, so the initial H+ is 0.05 m. Using the formula pH equals negative log of H+, we calculate the pH as 1.30. After adding 10 milliliters of sodium hydroxide. To find the new pH, we need to subtract the moles of NaOH from the moles of HCl, calculate the leftover H+, and then determine the pH. First, calculate the moles of H+ in the HCl. Number of moles, H+, Zax 0.05 moles per litre, times 0.05 litres, so 2.5 times 10 to the power of -3 moles. Then, calculate the moles of OH from NaOH. Number of moles OH equals 0.05 moles per litre, times 0.01 litres equals 5 times 10 to the power of -4 moles. After that, subtract OH from H+, leftover NaNH+ equals 2.5 times 10 to the power of -3 minus 5 times 10 to the power of -4 equals 2 times 10 to the power of -3 moles. Next, find the new concentration of H+. Total volume equals 50 milliliters plus 10 milliliters equals 60 milliliters equals 2 times 10 to the power of -3 moles divided by 0.06 liters equals 0.033 m. Lastly, calculate the new pH. Using the formula pH equals negative log of H+, we calculate the pH as 1.48. Next, when 25 milliliters of sodium hydroxide is added, we need to calculate the concentration in order to get the pH values. First, calculate the number of moles of H plus equals 2.5 times 10 to the power of -3 moles. Then, calculate the number of OH, where 0.05 moles per litre times 0.025 litres is equal to 1.25 times 10 to the power of -3 mole. Then, you need to calculate the excess of H plus by different, the number of mole H plus and number of mole OH, and you will get 1.25 times 10 to the power of -3 mole. Now we need to calculate the concentration of H plus total volume is now 50 milliliters plus 25 milliliters, equal to 75 milliliters. The concentration of H plus equal to 1.25 times 10 to the -3 mole over 0.075 litre equal to 0.0167. pH value can be calculated by using the formula pH equals -log 0.0167, and the final answer is 1.77. Lastly, the addition of 30 milliliters of sodium hydroxide. First, calculate the number of moles of H equals 2.5 times 10 to the power of -3 moles. Then, calculate the number of OH 0.05 moles per litre divided by 0.03 litres, equal to 1.5 times 10 to the power of -3 moles. Then, you need to calculate the excess H plus by finding difference of number of moles, H plus and number of moles, OH, and you get 1 times 10 to the power of -3 moles. Now we need to calculate the concentration of H plus total volume is now 50 milliliters, plus 30 milliliters equal to 80 milliliters. The concentration of H plus equal to 1 times 10 to the power of -3 moles over 0.08 L equal to 0.0125 m. Now to determine the pH values, we are using the same method like previously, which is pH equals -log 0.0125 equals 1.90. We can conclude that the equivalent point do not exist as the pH value is below than pH 7 after the overall addition of sodium hydroxide. The experiment is unfortunately unsuccessful. Finally, we can conclude that titration helps to determine the unknown concentration of an acid or base solution by neutralizing it with a solution of known concentration. Besides, we can determine the purity of a substance can be tested by measuring how much acid and base it contain, and lastly, by using pH indicator, we can observe how pH changes during a reaction to study acid-base strength. Thanks for watching. That's all from us.